Okay, so these are the results, typical results we got from our experiment. So you can see we've increased the length of the bar by 10 each time. We've measured the voltage in the current, but that's to allow us to work out the resistance here in the right-hand column. What you should do is draw a graph of length of the wire, our independent variable on the x-axis as usual, and resistance on the y-axis. If you notice here, both our voltage and our currents are the two significant figures. Therefore, when I do V divided by I, my answer should be the two significant figures. So for the first one, that means it should be 8.0, two significant figures. But for the second one, we don't put in a decimal place there because the 16 in itself is two significant figures. So plot those results on a graph and then check yours against mine, which is to the right. So if you pause it here, and then we can go through your graph. So you should have got something like this. Labeled axes with units, scale probably just about in both sides, taking up more than half the page. So if I go up in tens, I take up 5 out of 9 squares. On the x-axis, if I go up in fives, I take up 8 of 14 squares. So both those scales are okay. We then get our data that looks like this, and we should get a pretty nice straight line through the origin for these points. Okay, so if we draw a line, we get a straight line through the origin like that. There's a little bit of scatter of the results, but it's not a problem. The trend is definitely straight line through the origin, so we can make our usual conclusion that we make here. So as the length increases, the resistance also increases. And then we can add to that. So the graph shows a straight line through the origin. So length of the wire and resistance are directly proportional.